Okay, let's continue. So now we already know a lot of things. We know a lot of things about convex analysis. Let's see how these tools, how these principles may help us solve single-variate nonlinear programs. So pretty much we want to discuss about how to analytically solve single-variate nonlinear programs. Okay, so maybe some of you are not so familiar with the idea of analytically solving a problem. Somehow that means to express our solution as a function of problem parameters symbolically. So in the past, when we are trying to use algorithms to solve problems, for example, when we are using the simplex method to solve linear programs, when we are using a gradient descent to solve nonlinear programs, those problems are numeric or numerical algorithms. Okay, so in that case, our answers, our solutions is a number or several numbers. Okay, the production quantity, the price, and so on. So in those cases, we don't really have an analytical solution. Later, what we will do is that we will see that the answers are some functions of problem parameters. And now that means even if you don't give specific instance parameters values, we still are able to solve the problem and express the solution. So in this case, even though we solve problems with only one decision variable, we may still see some useful examples later for us to show that this is really useful. We will, in this case, focus on twice differentiable functions and try to utilize convexity if it is possible. Okay, let's see how to do this. So pretty much what we want to do is that we want to talk about twice differentiable functions, and we use that to talk about convexity. So when we have a general function, we may use the definition of convex function to talk about convexity. Okay, the definition is that when you cut with a line, that line segment should be above of that function. But if we always want to use the definition to do the convexity check, that may be too difficult or too tedious. So what we may have is that if we have twice differentiable functions, and in particular when they are just single variate, if we say they are twice differentiable, which means the second order derivative exists, then we have proposition 6, which is quite useful. It says that if your f is twice differentiable over an interval a and b, then in that case, your f would be convex over this region if and only if the second order derivative for all values in this region is non-negative. Okay? So we all know why that is true because we know calculus. When you have a function where the second order derivative is positive, that means the function is having an upward curvature because the slope is increasing. The first order derivatives are increasing. Okay, so that's why we have condition 1. And then x bar would be a local minimum over this region only if the first order derivative is 0. So why is that? Because if we have a twice differentiable function, then at all the points we may check is slope. We may check the first order derivative. So a point may be a local mean only if we have first order derivative 0, right? Otherwise, we may either move to the left or move to the right and then get lower values. That's not going to be a local minimum. The last condition is that if f is convex over a region, and then combining the first two, we would say that f prime of x star is 0 is going to imply that x star is a global mean, or the other way is also true. So what does that mean? That means if we already know that if f is convex, then local mean implies global mean. So if f is convex, then this condition gives us a local mean, which implies global mean. And also, a global mean must be a local mean, and a local mean must satisfy the first order derivative equaling 0. Alright, so this somehow illustrates how proposition 6 may be applied. Please note that the two boundary points may need special considerations. So that's why here we only talk about an open interval. Okay, so if we do not consider too much about the boundary points, or if our problem is actually unconstrained, then we would be safe in applying all of this. So the condition for a point to have 0 first order derivative is called the first order condition. For all functions, our first order condition is necessary for a local minimum. No matter how your function look like, if a point is a local minimum, it must satisfy the first order condition. And if you have a convex function, something like this, then first order condition would also be sufficient for a global minimum. Okay, it becomes sufficient, and it becomes sufficient for local minimum. So somehow that means if we have a convex function, convex objective function, if we are able to show that it is convex, then it would be really nice, really help us a lot in solving in an NLP, in finding a useful solution.